It's a real pleasure to be able to introduce the father of internet traffic analysis, Walter Villinger, who is going to talk about nails.
Okay, thank you, Rob, and it's certainly a pleasure to be here. When Sid Resnick asked me to give a talk in this workshop, he started to make me think about it, and so the thought was, what do I think is the most important lesson that we learned from the last 10 years of graph models of the internet, that we learned as internet researchers that people who work in the general area of networks should be aware of. And so this talk is basically my view of what that most important lesson or lessons should be. Quick outline of the talk is, so I talk about internet connectivity structures as they are generally being defined, considered, studied, talk about the corresponding measurements, and then just briefly describe 10 years of internet models or graph models of the internet. Come to some criticism of that traditional view that we have, and then contrast it with a view that is really very basic, but it's engineering based. And then give you one case study that goes all the way back to the measurements, and then uses the measurements to say there needs to be a new approach to do the internet model or graph models for the internet in particular, and that approach I will present a little bit, and that's an engineering-based approach. And then I conclude with some lessons learned. Here is my artistic rendering of an internet structure, and the internet is sort of nice because you look at this and say, yeah, this is a nice network, and then the only thing now, in order to define structures, I have to tell you what is a node, what's the meaning of a node, and what's the meaning of a link. And now in the internet we have this nice feature that I can give you tons of different meanings. So that means we get tons of different connectivity structures. That means we get tons of different nails. And then the question is, what is the hammer? And I tell you that as soon, also very soon. So example number one. What's a node? One connectivity structure you get if a node is something like this, and that's a router. So it's a physical piece of hardware that does certain things in the internet, certain critical things. And so the node is a router, links are physical connections, and you see these interface cards, and that's where these connections end, and you see a finite number of interface cards. That means already. So just I wanted to give you an idea that, so this is a picture of a node, meaning the node has a physical meaning, and every now and then you have to remember that the node meant actually this particular feature. The typical connectivity structure that people have been looking at then is router level topology of the internet. And if you roughly want to say, okay, how big is this system? Well, roughly in the millions. It really depends on what you mean by router, but of that order. So that's one connectivity structure that comes out quickly. That has been a topic of intense studies and potential controversies that a different connectivity structure that I tried to illustrate in a similar way by telling you first what is the node. A node is this. A node is a whole network. So in this case, it's a network, an internet service provider that provides service to users in Italy. It's a 3D plot in terms of density of users, where the users are, and you really quickly see the users are where the major cities are, and indirectly it also tells you that this network has a geography, and this geography also comes with, in each one of these spikes, there is a physical infrastructure there. So this AS has a physical infrastructure. That's where the POPs are. That's where the users connect. So this is what you should think about what the node is. Of course, in terms of abstract connectivity structure, we just think again, we just have a node. Links are business relationship between these different service providers. So in Italy, there may be 10 service providers. There will be various relationships among those, and they connect to other networks. So the resulting internet connectivity structure is known as the AS level topology of the internet. AS meaning these autonomous systems where the network, the internet should be viewed as a network of networks, namely a network of these autonomous systems. In terms of size, it's roughly 30,000 nodes. I don't tell you the links because that's another problem. One more example. The node is a user. So the resulting example is that the node is a user, links are friendship relationships, and then the resulting connectivity structures are these social media network graphs. Let's think of Facebook or YouTube, and I put the two examples for a purpose because in Facebook the friendship relationship is really something that you may want to think about a friendship relationship. In YouTube, the friendship relationship between users does not indicate anything about friendship. Okay. So these are just two contrasting examples that again you should keep in mind because social graph, online social networks have different meanings depending on what network you're talking about. So here are three types of connectivity structure that you can quickly get out of the internet by just telling you the meaning of what the node and the link is. Now the nice thing about the internet is also these structures come with measurements. Example one, so the router level topology, the measurement technique is traceroute. That's what traceroute does. If you don't know what traceroute is, I will tell you a little bit in a minute. Example two, the AS level topology, the measurement techniques are BGP tables. They yield the information that you think you might want. If you don't know what BGP is, then I hope you don't work in AS topology modeling because you should. Example three, overlay graphs. The measurement techniques are crawlings. You design crawlers that do the crawling of these large-scale networks in the most efficient way, and you get the information that you want. So the beautiful thing about this aspect is these measurements, experiments, large-scale experiments, large-scale projects that have done these experiments all over the world yielded measurements that are available publicly. So anybody here can download many of these data that have been collected, and you can study networks. The question is that the right thing to do? If I sort of spent some time trying to summarize 10 years of graph models of the internet in 2 slides. So the first slide just says you pretty much what has happened. If you look at these 3 graph structures plus others, one of the really driving forces for much of the work in this area has been this apparent universal feature of this data. Namely that if you look at the node degree distributions, they're just extremely highly variable. This motivated the generation of, or the development of a new class of graph models, which you may want to call the hammer. And that is the scale-free network models of the preferential attachment types, or all of its variations. And then, of course, the implications of these models have been extremely powerful in terms of simple models, in this case applied to the internet, produce extremely strong predictions. And the predictions go from extreme vulnerability to attacks all the way to extreme problems when it comes to spread of viruses and worms. And the most well-known property is this Achilles heel of the internet. You knock out these highly connected nodes in the center of the network that arise from these scale-free networks, and the network will fall apart. It's pretty much as bad as you can think about. So, just to give you a sort of a visual impression of what these networks look like. Here is just a rendering of a simple preferential attachment type graph. Here is a preferential attachment type model that has been proposed for the AS level internet. So now if you try to summarize 10 years of graph models of internet in one slide, here is a little bit tongue-in-cheek. The network scientists have been great in terms of, you give me this model, you give me this data that are available publicly, we'll model. Or we'll model for money, I think. Mathematicians. So these models typically didn't come with any rigorous proofs. And the nice thing about these models, of course, again, these are completely new, they have completely new features. So that means interesting math. And you know, the list of people who worked on this are really impressive. And we ended up getting rigorous proofs as far as these models are concerned. And then lastly, the networking researchers. So give me models, we will use them. But, so in some sense, you know, if you want to blame one community for what has happened, and as I will tell you soon what happened in the internet, blame the internet researchers because they have forgotten about anything they know about the internet and applied the stuff. So this is sort of a result of this, you know, if there is a hammer, you know, all the nails look the same. So what is the criticism that comes with it? Because so the criticism typically, I mean, started out with the internet researchers looked at these particular scale-free models that have been proposed for these various internet structures that I told you at the beginning, and yeah, that really didn't make sense. But why? So the criticism starts out with a realization, which is really very basic, and that says, you know, the discovery of the scale-free nature of the internet requires absolutely no domain knowledge. You didn't have to know that a node was this router. You didn't have to know that the node was this AS that has this internal structure. It was just a node. So details don't matter in this context. And of course, for engineers, that's a message that they don't like to hear because details are critical. Engineers are also proud of the fact that the internet is a highly engineered system. So they tell you, don't tell me that you can model it with a random graph. We don't toss coins to connect routers. We do it in a different way. And that's the point here. I mean, the randomness in these scale-free models or in these random graph models that came out of this work, the randomness comes explicitly through how do you connect two nodes. You flip a coin or a bias coin or something, and that determines how you do it. And then, of course, there has been this somewhat single-minded focus on this power law stuff. And the measurements that I told you about have been taken at face value. They are out there. You can download them. Don't ask where they come from. Just use them. And the philosophy has been, the more data, the better. And the fact that, you know, even the idea of checking the quality of this data and doing some sort of data hygiene has been a completely foreign concept. And it sort of goes back to where do these data come from? They have been measured, they come from computers. Computers are good at measuring. Well, they measure everything, even garbage. And that you have to remind yourself. And then model validation in this context really has been a joke. It has come down to my model is good because it matches a certain statistics from the data. And by the way, the data may be garbage. So what does that mean for the model? So then let's go back to the internet connectivity structure, to the nails, in view of this criticism, in view of the internet is a highly engineered system. So these connectivity structures, it's more than nodes and links. These structures that are out there have a purpose. They have a function. You cannot just build it any which way you want. There are constraints that come with this design of such a system, and you have to deal with some certain uncertainty. But one thing that you know for sure is the uncertainty is not by how you connect the nodes. The uncertainty comes from a different source. And if you get that source wrong, the models may not do what you think they should do. This is sort of a theme that I try to come back every now and then. It's sort of easy to state comment. The internet is a system that's driven by technological, economical, and social factors. What are these factors? And how many do we need to understand in order to get a good picture of the internet as a whole? And I will come back to that. And then, of course, the engineer's main message has been, look, these are not random networks, these are engineered networks. And just go through a couple of slides to illustrate briefly, to give you the flavors for those who don't work on the internet side, that yes, this is not a random system, but a highly engineered system. So if you don't know anything about internet, the internet to you might look like something like this. So you are on your computer, there is some server, and you get your stuff from that server, and you know it goes through the internet through some of these devices, and you don't care what these devices are, just let's call them router. Now contrast this with the engineering view, which says, behind this very simple view of the internet as just sort of a flat system is actually a whole layering architecture. And now you can already see now, in this layering architecture, each one of these layers defines a connectivity structure. So if you talk about internet topology, you already have to tell me more or less precisely at which layer are you talking about connectivity. Is it all the way at the HTTP or application layer, or is it at the IP layer, or is it down at the physical link? Now this complexity that comes with this architecture is there for good reasons. And of course the engineers tell you that these architectural details are the most important things to understand the system. If you have a model that does not point to any of these features, you should expect engineers to push back on you. Now, surprisingly, they haven't done much pushing back in the last couple of years, but I think it's slowly changing. So we have this nice vertical decomposition of the simple view of the network in terms of layers. And again, these layers are there for very particular purposes, and they have to be taken care of. They in particular enable the fact that any applications that you can come up with can run on any technology. You as an application designer, you don't have to worry about anything about how your service provider runs his networks with what technology. Because you have this one feature there, this IP level structure, maybe the protocol IP, where IP runs on everything, but every application has to run over IP. And that enables this beautiful, what's called the hourglass architecture of the internet, that enables you to write any application over any technology. And then take this view of the internet hourglass and talk about connectivity structure, then you can immediately come up with connectivity structure at the bottom. That's the physical connectivity structure, intermediate IP level connectivity structure. Here is also where the autonomous system structure comes in. And then on top of it, you can pretty much define any sort of logical connectivity structure based on the applications.
Sorry, connectivity, how do you use the word connectivity? You mean a graph?
In the web graph, for example, you have two web pages that are connected if they point to one another.
I'm asking about the word connectivity. What does it mean? You mean a graph structure?
Connectivity depends on which layer you're talking about. If you talk about connectivity at the level of autonomous systems.
I'll ask you later.
Okay. So the one thing that we can say about these various connectivity structures is that as you go from the physical to the application layer, it becomes more and more virtual. up there, the web graph is not a physical graph. Online social network graphs are not physical graphs. The physical interpretation is at the bottom, where you have the hardware. And then, the other thing that you can say in general about these graphs is the dynamics on the top. On the bottom, you have static infrastructure, almost static. They change slowly. On the top, these web graphs, online social network graphs, they change highly. They are highly dynamic. So this was the vertical decomposition. And then there is also the horizontal decomposition, where the internet as a whole is decomposed into individual pieces. And I already talked about these individual pieces, and that is basically, so if this is a rendering of the internet topology as a whole, this big spaghetti ball, this spaghetti ball is parceled into these networks. So the internet is a network of networks, which are these autonomous systems. And that leads then to this autonomous system graph. So two ASs are connected if they have a business relationship. So it's already a virtual graph. It's not anymore physical. And in this context of the S-level topology, you have to remind yourself that you can have a simple graph like this, but its physical realization can be something like this. So it really obscures physical connectivity. And the AS graph also obscures geography. So as I showed you here, a simple node is something that you have to remind yourself. A simple node is like something like this. And then if you think of, I don't have a picture for that, but in the US you have this similar thing that you have multiple service providers across the whole country, and then you have to think about the internet, the AS level graph of the US. Just take the tier ones for, it's really a pancake. It's not a graph in the usual case. So then we go to this notion. So what sort of physical connectivity structure really makes sense to study? It doesn't make sense to study the internet router level topology as a whole, because as I just showed you, there is internal structure. And so what makes sense is to study the router level topology of individual networks, so of an individual AS. So the routers are now the switches, the links are the physical connections, so the physical links that connect two routers. And then what we are aiming for is a formulation of this system as a structure where the technology is the most important thing to be captured, some economic aspect, and a rudimentary form of social aspect. And I show you how we do this. So this is the one case study that I will do later on. The second example goes back to the AS level topology. Again, same thing there, except now we want to formulate it again as a system where now not technology dominates, but economics dominates. And how we exactly do this, we have no idea yet. But there are indications that we may be able to get there. And on the overlay side, we really want to formulate this one as a system where the social aspects dominate. And economics and technology play some role, but a secondary role. And then as the internet as a whole, you can sort of think it's the combination of those three pieces really in an abstract way, where technology, economics, and social aspects play a role for the whole system to work the way we see it operating today. So the case study I will show you for the rest of my talk is example 1 prime. How do we do inference? Or what are the measurements that are available for trying to do inference for router level connectivity of an individual AS? And how do we go about modeling that connectivity structure? So what are the measurements? So as I said, measurement tool is traceroute. Traceroute is a simple tool that anybody here can use. You can type traceroute and give an address or a web page or whatever, and you get something like this. So I did a traceroute from home to Newton Institute, and you get a bunch of things that look like, each line gives you basically, or is an indication of the router through which that packet went through. So I'm in New Jersey, here is Newton Institute. There are about 19 hops at the router level that the packets go through. And of course, if you do this now, if you have many friends, you do traceroute from all the friends to all their friends. It gives you sort of an idea. Maybe it's possible for you to glue together these pairs and get the router level topology of an AES. Now, you have to remind yourself is traceroute is first of all strictly about the IP layer, which I showed you is sort of sitting in the middle of the layering structure. It was developed in 1988 for one particular purpose, and that is just the idea was at that time I would like to know how my route from one place in the internet to another way looks like, and that's the only purpose for which it was designed. Traceroute was not designed to map the router level topology of the internet. Never. Since it wasn't designed for that, you shouldn't be surprised that it doesn't exactly do what you want to do. So using traceroute to map the router level topology of the internet is really an engineering hack. And it's a beautiful example of reminding yourself that what we can measure is not what we would like to measure. And in that little difference makes a whole big difference. So now I have to become a little bit technical because I have to point out that these data are essentially useless to infer router level topology. Big problem is what's called the IP alias resolution problem. So in this traceroute example I showed you, each line indicated, oh, this is the router through which my packet went through. No, it's not the router, it's the IP address of the interface of the router. And routers have potentially many interfaces. And we have no way to map interfaces to the router. We don't know how to do it. So there have been attempts to do it. There are heuristics out there, but some heuristics work in some scenarios, some do a lousy job in other scenarios. And the result is, at this point, we have no good way to map interfaces to routers. Now, why is this a problem? So here is a tiny little illustration that, so here is the real network. You do traceroute from those two top points, and it goes through these two interfaces. If you don't know that these two interfaces are at the same router, the network structure is something that you get is the one on the left, whereas the right network structure is the one on the right. So does this really happen? So Evelyn is always a little test case. So we have Evelyn, very simple connectivity structure. How does the top of the line mapping technique based on traceroute deal with Evelyn? What does it produce? So I'm afraid that the resolution won't be very good, but this is what it produces. This doesn't look like anything like Evelyn. It has, I don't know, a factor of 10 more, or a factor of 10 more nodes, and it has a factor of, I don't know what, more links. It has, this structure is absolutely not the same as this structure. But that's what the traceroute data give you. So you should, seeing this example, you shouldn't be surprised that using traceroute to infer router level topology of a AS is very misleading. And essentially, you cannot use them. Just to illustrate, if you're interested in the node degree distribution, see the difference. The real one versus the one that comes from the inferred that people studied. Completely different. Now, if you think that traceroute has only this one problem, it has another problem. There is something called layer 2 technology, which is essentially a circuit layer technology that makes internet paths disappear from the IP layer, and it makes the following picture. If this is the router level topology of my network that I want to discover, this layer 2 technology forces traceroute to give you this picture here. It doesn't say anything about the internals of the network. Does that really happen? Here is an example. State-of-the-art mapping tool of a ISP in the US, a tier 1 ISP, gives you this picture here, and you say, wow, this is high connectivity. But the result is that this is a precise example of an ISP that uses this layer 2 technology that says nothing, that lets traceroute say nothing about the internal structure of the network. So the use of traceroute, of a readily available technique that anybody can use, which makes it so appealing to use it in this context, ends up being sort of a very bad thing to do. And the irony is really that the high degree nodes that in the network that traceroute gives you are not for real. They are due to this example, some of these examples I showed you. On the other hand, if there are high degree nodes in the network, the technology that's out there today enforces that these high degree nodes would be at the edge of the network. And no general purpose traceroute, large scale traceroute experiments would ever discover those high degree nodes at the edge. So here you have traceroute that finds high degree nodes that are not real. If there are high degree nodes out there, it will never find them. So that's a bad scenario. And if you think that's the only problem with traceroute, there are other ones. But again, there is sort of an irony there that so people have pointed out that traceroute has an inherent bias, or at least some mathematical abstraction of traceroute has an inherent bias. But of course, in the presence of these tremendous systematic errors, this bias is really a non-issue. Forget about it. First, solve these systematic problems, then deal with the bias. But as I said, at this point, we have no way of dealing with these systematic errors that destroy any credibility that traceroute measurements have. So the bottom line of this little data hygiene exercise is, here are these large data sets of traceroute measurements out there that anybody can use. And you have to say, if I'm interested in trying to infer the router level topology of a network, I cannot use it. Forget about it. Throw it away. At some point we may do a better job, but within the near future, it doesn't look like that will succeed. So the lesson learned here is really start, if you are given a data set that you want to use for your purpose, start with this question: can you trust the data? And that points out the critical role of data hygiene in the age of these large and larger data sets. Because unfortunately, data hygiene is not viewed as a very glamorous work. But you have to remind yourself that if you have garbage and you have lots of garbage, you still have garbage. And traceroute data is an example that in the context of how it's used, you have to view it as garbage. And it's not the fault of traceroute. It's the fault of how it has been used. And by the way, in this context, you realize very quickly, because of this complete unreliability of traceroute to infer anything, power laws are non-issue. They are off the table, as they should be, because the data do not justify anything. Now you say, what now? Now I have no data. I still want to model. So I cannot use the data, but I still would like to come up with a model. So what's the solution? There's sort of only one solution, and that is use domain knowledge. I like the phrase that Frank Kelly told me the other day, go native. You have to learn about the domain. Once you learn about the domain, then you can start applying an engineering perspective to this highly engineered system, which is, makes complete sense. It's a highly engineered system. You should apply an engineering perspective, not a random graph perspective. How does this engineering system work, roughly? It starts with this observation that I made already. Surely the way we design a network is not by tossing coins. The ISP designs their network for a purpose. Roughly, what is the purpose? So I know this is not a precise purpose. Different networks have different purposes. But roughly, this is more or less what's going on. You design a network to carry some traffic. Hopefully, you carry it profitably. You make some money. So the purpose as general is not that easy to infer. So randomness comes in not in the way you connect nodes, but uncertainty is in terms of what demand should I carry. Here is a network designer who has to design a network that's in place for the next 10 years. He has to deal with the uncertainty in the demands. That's where the uncertainty comes in, not in how I connect the routers. In addition, the ISP cannot just go out there and buy anything. They have to buy what Cisco offers, or Juniper, or your favorite vendor. And it has to satisfy some economic constraints. Long links today are still expensive. You stay away from them. So once you have formulated this engineering perspective in this sort of very obvious and intuitive way, then quickly the design aspects, so designing an internet, router level internet for an ISP or an AS, comes down to you have an objective and you have constraints, and you try to come up with something to deal with this trade-off between what's feasible and what is desirable. And so you have an optimization problem. So suddenly, instead of a graph formulation, we have a constraint optimization as a mathematical modeling language. And in this whole engineering approach, the power law issue is gone, as it should be, because the data don't justify anything. So this is just an illustration of why the ISP has to satisfy certain constraints. At any point in time, this is a little bit old, a couple of years old. In this case, Cisco, take your other router vendor. The top of the line router that you can buy, the most powerful router, has physical constraints. In this case, you can only connect 16 high-speed links with this router. So connectivity of this router, at most 16 if you use it in a certain way. And so this is a gigabit per second router. Today we have terabit per second routers. So it's just increased, but the finiteness in terms of how many interface cards you can plug in here remains. So if you use it as it comes in its most efficient way, the maximum degree that a router can have in your network is 16, if you use Cisco at that point in time. There is a way to sort of increase the connectivity slightly by one order of magnitude, but you take a performance hit. And then you ask yourself, do you use the top of the line, most expensive piece of equipment that's out there in the market in its least efficient way? And any engineer that does it would have to justify that. And here's one slide that illustrates what this engineering approach does in terms of a heuristically optimized topology design that is based on this perspective of we build networks for a purpose, it has constraints, and you have to deal with the uncertainty in the environment. And step number one is the technology constraint. Step number two is some model for the uncertainty. So you have to pick some traffic demand matrix that tells you how much demand goes from where to where, or what you expect. So that's the uncertainty. And then you pick some objective function. And here's a simple one where you say, push as much flow through the network as you can, satisfying the requirements that come with the router constraints. And if you solve this problem, and again, I don't mean solving in an optimal way, a heuristic way is more than good enough, then what you get out is something that looks like this. In the core, you will put your top of the line, most expensive routers that have the least connectivity, and at the edge, you will put up the less expensive routers where you can increase the connectivity. And then if you get a design that way, you get the top left picture, and you compare it with the random construction. And in this case, these two have the same node degree, if you are wondering about what the node degree is. And from a random perspective, of course, the left-hand example will happen with probability 0, or with very, very small probability, because it's an example of a highly designed network, not a random network. And then if you try to compare the two things, with respect to pretty much anything you can imagine, the designed network is completely different from a random network, and it's not surprising because it has been designed. Let me finish up with some implications of this engineering perspective. So the lesson we learned is, first thing, so this is, if you ask me what is the most important lesson that we learned from 10 years of graph models for the internet that other areas should know about, is know your data. Because as I showed you, there will be times, and the internet is only one example, there will be times where you have to say at the end of the data hygiene effort, throw away the data because I cannot use it for the purpose that I want to use it. These simple models that have been proposed are extremely appealing because they are simple and they look convincing, but unfortunately, you can turn it around, and so this sort of more engineering perspective provides more new opportunities. And unfortunately, this also shows that details really matter. You cannot design an engineered system and say, don't worry about the details. Or if you do so, then you end up with something that doesn't work. And the two paradigm shifts I think one has to keep in mind is, so network modeling really has gone from an exercise in data fitting to an exercise in reverse engineering. You have a system out there, first question you ask, once the data issue is dealt with, what's the purpose of this network? So that's an interesting question with respect to pretty much any network that you can imagine. And in terms of mathematics, we really have moved from the graph theory modeling to constraint optimization as the modeling tool. So if you want the essence of this engineering-based approach, a couple of observations. This approach makes matching any graph statistic, for example, node degree, a non-issue. This is not the goal of modeling. And as I pointed out, the reason is, there are good reasons for it, because very often the data is so bad that it doesn't let you do this. Or there is no point in matching anything. And the example of the node degree distribution has been a convincing one. The only real alternative is to go native. Learn the domain, bring that domain knowledge to the design of the system. If you do it that way, then completely new opportunities arise immediately. This is one of them. Now we can suddenly start studying dynamics of these networks and over these networks, which didn't even arise in the context of the random models that have been proposed. So traffic dynamics and routing has an impact on the network structure, and the network structure has an impact on the traffic. So there is an interesting feedback behavior between structure and traffic, and you have to start telling you cannot study traffic over these systems without knowing the structure, and you cannot study the structure without knowing the traffic. And that opens up a whole new arena of topics. And then ultimately, in terms of model validation, what model validation really should boil down to is, somebody gives you a model for whatever you ask for, and you always should ask a question, what kind of new measurements does this model suggest that you have never taken in your system in order to demonstrate that your model is really valid? Okay, last slide. Sorry. Just a couple of comments here. So on network modeling, in the presence of high volume, poor quality data that cannot be taken at face value. There's this nice saying from Mandelbrot that says, so when exactitude is elusive, it's better to be approximately right than exotifiably wrong. And the last 10 years of network graph models for the internet have been an example of what can go wrong, and I think we are moving away from that to be approximately right. And then as far as scalable networks of the preferential attachment for the internet, and let me state it. So all that I said about this stuff is the application of this class to the internet. You have to sort of say, this is one of these examples where the slaying of a beautiful hypothesis by an ugly fact. Traceroute is an ugly fact, but it is an effect. And that the bottom line is that this data cannot be used, is a a consequence of the effort that goes in here trying to take these data sets and ask the question, can they be used for the purpose for which you want to use it? And that the answer is sometimes no is maybe too bad, but at the same time it provides unique opportunities for moving on. Thank you.
You have rightly said in the conclusion that things are from the textbooks and all that. Do you know somebody who is working on reliability of the internet? Because in the banks, etc., most of the time we find that the internet is not working, server is not working.
So, first of all, the internet is probably one of the most reliable networks that you can imagine. When it doesn't work, there are reasons. If you take this perspective of the engineering perspective, so if there is a reason, the engineers will figure out where it is, but now you also see in terms of the architecture that the reason why, when it doesn't work, why it doesn't work, there are many potential sources. And so it becomes a complex issue. So it's not anymore a simple case of the internet doesn't work because this node failed. There is more to it than a node failure. It's way more complex. And this perspective opens up again a completely new arena for studying the reliability or the robustness of the internet, because it now points towards this very complex structure that can be where you can start to get your hands on, and it's possible to do it in a way that now makes sense. It's not anymore just connectivity. There is more to it.
Just want to applaud from a statistical perspective what you're saying. It's a very important message. Secondly, I'd just also like to comment, there's a parallel development in the study of human sexual net networks. Any attempts to fit preferential attachment and parallel models to the number of sexual partners that individuals have. And in there, the issues are some of data measurement, the recall biases and other issues along with the elicitation of it. But also for a long period of time, the lack of valid statistical fitting of these models using eyeball methods to justify them. So my point basically is that this process, although you've made a very clear argument for it, occurs in many other areas for different and sometimes related reasons.
I mean, I appreciate you pointing that out. I feel comfortable talking about this in the internet context because I know what I'm talking about. I have seen indications of it in other areas as well. And one of the other areas is also biology, where sometimes biologists come and say, if you think you have problems with the measurements, come to us. We have even worse problems. And yet these data are used exactly the same way as you talked about. So that's why I thought maybe this message of look at the data first is something that people in this domain should take more serious.
Take one more question.
I'm delighted to hear that you say that these models have nothing to do with reality. But I don't think you will find a single mathematician worth his soul who didn't know it all the time. I mean, the starting position was that there was this article in Nature which said that graphs appearing in Nature look random because I don't see any structure in them, but they don't look like the Erdős-Rényi graphs. I mean, that was shocking nonsense. I mean, of course not. That's not why Erdős-Rényi invented it. These are all mathematical structures. So one could say that all of percolation theory is rubbish because the connection with reality is minuscule. But the study of percolation has completely different aims. The very vague motivation comes from physics, but then mathematics takes over.
I understand. So I'm completely in agreement with first of all there was a motivation that pointed towards the study of new classes of graphs.
That's it.
It's great.
And as far as mathematicians are concerned,
that's great.
That's it.
Yeah, but you have to admit there have been many attempts by the mathematicians to say
no. These are the people I would not call mathematicians.
Oh. Okay.
And I could tell you lots of problems arising in terms of
Okay, so-
in connection with these models,
Okay.
which are extremely interesting as mathematical
yeah,
questions.
yeah.
And I give you 50 years to do them,
Yeah.
and I bet you will not.
Of course, yeah. I'm fine, I'm glad that
very
you.
deep questions and connections with other branches of mathematics.
I'm glad that you helped me to gave me a criteria to distinguish between mathematicians and non-mathematicians.
You should.
Okay, well, let's thank Walter again.